Chapter 6, Section 4. We're on to parallel lines and proportional parts, or as I like to call it, Unit 1 returns. Take a look. We're going to be looking at a lot of parallel lines today. So things like corresponding angles, alternate interior angles, all that kind of stuff is going to come back to bite us. So if you need to go back and take a look at our parallel line work from Unit 1, do that. Because again, a lot of parallel lines, a lot of parallel issues going on here. Heads up. So let's get started. What we're looking at are situations like what you see here, where we're dealing with triangles and parallel lines that are somehow cutting that triangle up. So the first thing we're going to look at is called the triangle proportionality theorem. Here's what it says. It says, look, if we've got a line like BD that's parallel to one side of our triangle and intersects the other two sides in two distinct points, so for example, B and D in this case, then it's going to separate the sides, so for example, side AC and side EC, into segments of proportional lengths. So take a look. Let me grab another pen color here so we can kind of keep up with this. So for example, if I'm looking at BA, so here's segment BA, and segment CB, so let me color that there, CB. So notice that parallel line has broken this side up into these, we'll call them red and blue segments. We've got DE on the other side, so this shorter segment, we'll put it blue, and then CD, we'll put in red. So what it does is it separates the sides of the triangle out into these little segments, and these segments form a proportion. So BA over CB is proportional to DE over CD. And again, what this will help us do is it'll help us figure out different measurements that we are missing, knowing that this proportionality works, provided that these parallel lines are here first. So let's take a look real quick at a proof. How do we know that this actually plays out? So notice what the book has done here is it's taken the same diagram. The only difference it's made is that it's put angles 1, 2, 3, and 4 in here instead of us having to use this alphabet soup. So take a look. All we know at this point is that BD and AE are parallel to each other. Our job is to prove that BA, so let's color that in again, BA and DE, okay, these two segments are indeed forming a proportion with CB and CD. All right. And we're going to do this kind of loosey-goosey. We're not going to get super formal. It will be 2-column, but we're not going to get too overly excited here about what we've got. So statements, reasons. There we go. And as we're going through this, again, we're going to try to keep it loosey-goosey. We're not going to get too technical here. So first thing let's do is we'll put out our givens. So in this case, BD being parallel to AE. And of course, we know that's simply a given statement. So we'll go ahead and get that down. There we go. All right. The next thing that would probably be good to do is to recognize that we've got two similar triangles here. For example, I've got triangle CBD and I've got triangle CAE. We need to show that those triangles are congruent. So take a look. I know that 1 and 4 and 2 and 3, respectively, are congruent to each other, and we know that because of corresponding angles. So let's deal with that first. So statement 2, I can say that angle 1 is congruent to angle 4. I can also say that angle 2 is congruent to angle 3. Make sure I'm reading that right. And our reason there is the corresponding angles. I think your book referred to it as a theorem, postulate. It doesn't matter. Corresponding angles, we'll say postulate. I think that's how it worded it. There we go. And remember, we got parallel lines. 1 and 4 correspond, 2 and 3 correspond. And since we got those parallel lines, we know those angles are congruent. So we now have a top triangle and then this larger triangle. All we need are 2 angles to prove that they're similar. So let's do that next. So statement 3 is that we've got triangle, let's go with the larger one first, ACE, ACE, is similar to triangle BCD. Try and keep it alphabetical there. And our reasoning is quite simple. Our angle similarity. All right, now that we've got that together, remember that we can say that side lengths of corresponding side lengths of triangles form proportions. So let's do that. So statement 4, I'm going to look at, how do we want to go about this? I guess we can go larger to smaller. We'll go that route. So I could say, for example, that CA, all right, so this side here, and CE, this side here, so we'll match those up. There we go. That those form a proportion with the smaller triangle. So in this case, CB and CD. D is in dog. All right. And we can say this quite simply. This is just what it means to be similar. In this case, what it means to be a similar triangle. So we could say what it means to see definition of similar. We could say similar triangles, similar polygons. We'll say similar polygons. I guess it doesn't matter. There we go. All right, now that we've got that together, remember, we're not trying to prove large triangle to small triangle. We're not doing that. We're trying to prove these individual parts. So what I'm going to do is I'm going to take side CA, and I'm going to use the segment addition postulate to break it up. So that way I get these individual pieces. So in statement 5, I'm going to take CA, and I'm going to break it up. So that way I can write it like this. I could say that BA, the smaller segment, added on to CB, all right, because remember, that's what CA is worth, right? That whole thing, over CB, alphabet soup's getting thick now, is equal. Let's do the same thing to the other side. So we've got this short side, DE, added on to the smaller side of our triangle here, so CD, and that's all over CD. So again, just to review, CA, this whole side, I broke it down into its individual parts, all right? CE, right, this whole side, I broke down into its individual parts. And our statement for that is simply the segment addition postulate. Cool. Now, I'm going to break this up. I can take the BA and the CB and I can separate those into two distinct fractions. Right now it's a sum, and I'm going to break it up. All right. So 6. Here we go. I'm going to write BA over CB added to CB over CB. Because notice, when we're adding fractions, the denominator doesn't change. So if I were to add these two fractions, it would look like this. It would look like BA plus CB over CB. So all I did was separate that out. We'll do the same thing over here. DE over CD added on to CD over CD. And again, we could say that's simply a substitution step. All we're doing is rewriting that addition out. So we took it from here, it's just a substitution step. I notice I've got CB over CB and CD over CD. Well, that's a fancy way of talking about the number 1. So let's do that. BA over CB plus 1 is equal to DE over CD plus 1. That's another fun substitution step. Substitution. There we go. I can spell. From there, we need to subtract, right? So I'm going to do the subtraction and then rewriting step all in one. I'm going to subtract 1 from both sides. So last statement 8, and then I'm also running out of paper. We've got, let's see, what do we got here? We've got BA and CB. We subtracted 1 from both sides. So those are gone. And then we've got DE over CD, which is what we were trying to prove. And we can simply write that last statement as a substitution. Again, substitution / subtraction, call it what you will. But that gets us a proof of what we're dealing with. Again, we're not comparing the side of the small triangle to the side of the large triangle. We're comparing these individual little sections. So they are indeed forming a proportion. We just showed that it worked. All right? So I'll leave that up there for just a second. If you need to pause the video, pause it. Otherwise, we'll go on. All right, well, let's take a look at the converse of the proportionality theorem, right? Our triangle proportionality theorem. And this is basically the same thing in reverse. It says, look, if we've got a line that intersects two sides of a triangle, and we look at those separate parts, right? For example, the AB and the DE side, and we look at the CB and the CD side there. If those form a proportion, cool, then we know these segments are indeed parallel. And by default, we would also know that the larger triangle and the smaller triangle are indeed similar. All right, so the converse would allow for that as well. Cool. Mid-segments. This is my favorite part. I like mid-segments. I can't tell you why, I just do. Here's what a mid-segment is. A mid-segment of a triangle is a segment whose endpoints are the midpoints of the two sides. So for example, BD in this case is a mid-segment. B is the midpoint of AC, and D as in dog is the midpoint of EC. Because of that, notice here on the left side, it breaks up AC into equal parts. It also breaks up CE into equal parts. And that provides us the triangle mid-segment theorem. Try saying that 3 times fast. Here's what it says. It says if we've got a mid-segment of a triangle, and it is parallel to one side of the triangle, and not only that, its length is 1/2 the length of that side. So let's go back. If I've got a midpoint of one side, midpoint of another, we play connect the dots, it's parallel. So BD is parallel to AE. And to add insult to injury, it's also 1/2 the size. So for example, if AE here was 8 units long, then BD would have to be only 4. Now, we can do a proof for this. It gets kind of involved, but let's do it long story short because we already spent some time with that other. Here's how we know it works. We just saw with the, let me grab my paper here, our triangle proportionality theorem, right? Excuse me, not the triangle. Where did I put it? Here we go. The converse of the triangle proportionality theorem says, look, if I can get a proportion out of these segments, and I would be able to, for example, let's give these some side links. Let's say this is 5, so this is 5. And let's say, I don't know, that this is 6, and that this is 6. I don't know, I'm making it up as I go. I would very easily get a proportion with that, right? I could say 5 to 6, and then 5 to 6. Of course, it's proportional, which would mean these are parallel. So proving the parallel part, that's easy. Proving the side lengths are 1/2 is equally easy. Take a look. We know that these two triangles are similar, right? We've got a similar angle here, right, in C. Now that we've shown that they're parallel, B and A are the same. So cool. We definitely know that they're similar. 5, 6, and 4, 10, 12, and of course, this would then have to be 8. So again, real quick proof of why the mid-segment theorem works. Super simple, super fast, but there it is. So lots and lots of different things going on in this particular section. If I can get my page to turn, love mid-segments. Put a star beside those. People always end up forgetting about mid-segments. Love them to death. Corollaries. Oh, love these corollaries. There are 2 of them here. 1, 2. Love this stuff. Take a look. If 3 or more parallel lines intersect 2 transversals, so here are our 3 parallel lines, if they intersect 2 transversals, they cut off the transversals proportionately. In other words, if we've got DA, EB, and FC all parallel, then AB, this segment here, across from DE, this segment here, that forms a proportion with BC, and then, of course, EF. And you may think, wow, that looks really familiar. Well, it should, because it's basically a rewriting of what we've got here. Take a look. Eventually, those 2 transversals will hit, they'll form a triangle. And basically, this is a rehashing of the triangle proportionality theorem, where we know we've got parallel lines, so ta-da, there they are, and then it breaks up those segments into perpendicular, proportional parts. Hence why it's a corollary. Remember, corollaries are theorems that come about because of other things. This is a direct cause, or this is a direct result of this, all right? The triangle proportionality theorem allows for this to happen. So if we can prove this, well, then proving this is pretty simple, right? Not all that complicated. Now, let's take it a step further. And we might separate these two, guys and gals. We might separate these two because these aren't, I mean, they're sort of related, but not exactly. If 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So let's talk about that. So if we've got our 3 parallel lines, so I'm going to redraw this situation. So 1, 2, 3, and they're all parallel. And it says, look, if they cut off congruent segments on one transversal. So let's get a transversal drawn. We'll draw it, I don't know. Who cares? We'll draw it right here. All right. If these segments that it cut off are congruent, so this segment and this segment are congruent, okay, then it doesn't matter what happens with any other transversal, they'll get cut off equally as well. So let's draw another transversal. And this time I'm going to draw it in, let's see, do I have a green? Yes, I do. Let's draw green. Boom, there it is. There it is. These segments are then congruent to each other. And you may be thinking, wow, that looks kind of familiar. Where have we seen that? Well, again, it's a related to, oh gosh, where did it go? Where did it go? It's related directly to the mid-segment theorem. I'm not saying that what we have here is a mid-segment, but it's based on that same idea, that because these are equally spaced because of midpoint there, then that's ultimately going to create, there it is, ultimately going to create these sections that are the same. So again, hence why they're corollaries. They're loosely based on a theorem that's come before it. I know this is a lot, folks. Keep it in mind. Be thankful that we're in NTI right now. That way you've got your notes handy when you're doing your work. If you are not doing your work with your notes at hand, I'm not sure what you're doing. All right, so use that tip. All right, let's look at a couple quick examples here. And we'll finish for the day because I'm looking at time and we're kind of running over. So take a look. First example here, number 16, I pulled out of a textbook. If DB is 24, so let's write that in, 24, and AE, all right, so this little segment right here is 3. EC, the sign down here, is 18. We need to find 80. So I'm going to put an X here to represent that. So remember, because we've got these parallel lines, these segments break up into a proportion. So I could say X, whoa, that's too long of a line there, in 3. And then 24 and 18. We can use cross products to figure this out pretty quickly. And again, I'm not going to multiply the 18 by the X just because I'm eventually going to have to divide it. So what I'm going to do is rewrite it this way. It's simple to type into a calculator if you're not sure of the exact answer. Plus, it saves you a step. So 24 multiplied by 3 divided by 18 gives us a fun answer of 4. Simple. All right, let's try another one. We're asked to find X in this case. Okay, so I'm going to circle that. Don't want to forget that. And I want to find ED. Where is ED? There's ED. If AE is 3, so let's write that down. AE is 3. AB is 2. Excellent. BC is 6. And ED is 2x subtract 3. So this problem basically works the same way as 17, the slight difference being we got an algebraic issue going on. So 3 and 2 are related. And then the 2x subtract 3 goes with the 3 there. They're on the same side. And then our 6 goes here. Wonderful. So let's do some cross products real quick. 3 times 6 is 18. 2 times 2 is 4. 2 times 3, in this case, a negative 6 because it was a negative 3. Let's add 6 to both sides. That is 24 and 4x. Once we do a little division, we find that x is 6. Cool. So we did that. We found x. Now we also need to find ED. So let's plug it back in. 6 into 2x, so 2 times 6, subtract 3. That's 12, subtract 3 is 9. Cool. And again, if you're not sure about how this stuff works, folks, ask questions during our class meet. We'll be good. Let's take a look at 2 more. Notice this section has been broken up equally, so this is a midpoint. Section has been broken up equally. This is a midpoint. In other words, we have a mid-segment going on. So we're asked to find x and y. Well, I noticed that these two are the same, so let's solve that real quick. 3y subtract 9 is equal to 2y added to 6. Subtract 2y, that's y. Add 9, that is 15. So cool. Y is 15. That was easy. Remember, mid-segments are half the length of what we have here. So I could say 5 over 3x plus 11 is equal to, remember, this is half as much, so I'm going to have to multiply it by 2 to make it equal to that base. So in this case, 2 multiplied by x added to 2. Let's work that out. 5 over 3x plus 11 equals 2x added to 4. Cool. Real quick, I'm going to make my life easy because I don't like thirds. Thirds are terrible. I'm going to multiply everything by 3. And what that's going to do is that's going to eliminate that fraction for me, and I don't have to work with that. I just don't like thirds. So we'll end up with 5x, 33, 6x, and 12. And yeah, they are slightly larger numbers, but notice how close these are. It's going to make my life easier. So let's subtract 5x from 6x. That gives me 1x. And let's go ahead and subtract the 12 from the 33. That gives me, what is that, 21. Excellent. So x is 21, y is 15. No harm, no foul. Take a look. We've got 3 parallel lines. One has broken it up evenly there, so those segments of that transversal, which means these are also going to be broken up equally. So solving this won't be too big a deal. Let's start on this side. 2x added to 3 should equal 6 subtract x. We'll add x to both sides, so that's 3x. We'll subtract 3 from both sides, that's 3. X is then 1. That was simple. Let's try this last one. Again, notice it's broken them up equally, so we know that these are equal. So 4 over 3y plus 1 is equal to 2y. And again, I'm going to do the same trick I did over here. I don't like thirds, so I'm going to multiply by 3. That gives me a 4y added to 3 equals 6y. And notice this is going to make my math easy. We'll subtract the 4 on each side. That gives me a 2y is equal to 3. Divide by 2. Y is 1.5 or 1.5. Whatever you'd like. So this is the kind of work that we'll be doing today. If you've got questions or concerns, again, bring them with you to class. Otherwise, have a good day.